Good evening, everybody. This is our introduction to, or at least our practice solving problems using Hess's law. It's one of the more complicated ways of solving for enthalpy, so let's get started. What I'm going to do today is I'm going to run through the solutions for all the odd problems on your homework. And that maybe help you kind of understand some of the logic behind them. So in this problem 1, the reaction for the combustion of butane is given below with all these coefficients. Now, when you're given an enthalpy in this guard, or in this way, where it's a reaction next to it, it means this is how much energy you get when you do the reaction exactly like this. So when you have 2 moles of butane with 13 moles of oxygen, 8 moles of carbon dioxide are produced, and 10 moles of water are produced. And when you do that, 2 of these with 13 of these, you get this much energy for every one. So this can actually be written as kilojoules per mole, assuming that these are all the ones they have. Now that can be a little misleading, this per mole thing, because it's not actually per mole, in this case, per mole of anything. So let's answer these questions. How many kilojoules of energy are released per mole of butane? Well, this is the energy released for if we had 2 moles of butane, so half of this would be for 1 mole of butane. So this would be I'm not going to do the math here. So 434.45 kilojoules divided by 2 moles, and that would give us the 1 mole. You can do that math on your own. That's for 1 mole of butane would be half of this amount. 1 mole of oxygen used. So if you used only 1 mole of oxygen, you would use way less than 1 mole of butane because it takes 13 moles to just use 2. So here we would have this same number, 4,345 kilojoules, and instead we divide it by 13 moles, and then we would report this as kilojoules. This one would be kilojoules per mole of butane, and this would be reported as whatever that number is, kilojoules per mole of oxygen. And we'd keep doing this all the way through. So if I want to know for 1 mole of CO2 produced, I want to know how much energy would be given off, then we would be looking at negative 4,345 kilojoules per, or divided by 8 moles of CO2, and this would equal, some kilojoules per mole of CO2. So for every mole of CO2 produced, you'd make this many kilojoules and whatever that number is. And the same thing here with water. So this one we can do actually, because it's divided by 10, so it looks like it's going to be negative 434.5 kilojoules per mole of H2O of water. So that's how you would take this delta H, this enthalpy of reaction, and break it into a molar enthalpy for each of the different products that are there. And that's true of all enthalpies of reactions. They are meant to be as the equation is written, and to figure out how many kilojoules per mole you would divide by those number of moles. All right. So this reaction has a negative delta H. So that means its enthalpy is decreasing. So it's having a negative change. So it's giving off energy, which means this is going to feel hot because our hand is going to heat up as it cools down, or as it gives off heat. The products contain less energy than they did before. They turned that stored chemical potential energy into thermal energy, and then that went out into the environment, the surroundings. This also means that the products are, so if they have less potential energy, they are now more stable. It's one of those things that are counterintuitive. The bonds will, to give off energy, these bonds must be snapping tighter together, and that snapping is what heats things up and gets them moving faster. So it has more stable, and on average they have stronger bonds. Again, stronger bonds mean they snapped closer together, converting that chemical potential energy into kinetic energy, and that they are closer together. That's tough. Anytime you pull bonds apart, remember, as they get whacked and the atoms break apart, as they're moving apart, they're slowing down because they're still attracted to each other. So they're slowing down, turning that kinetic energy they absorbed from a collision into chemical potential energy. And so whenever they come back closer together, they're speeding up as they pull each other closer together. And when they collide, they snap into that bond. They turn that extra speed into thermal random kinetic energy. And that's how things heat up. So number 3 follows up on 2, that boiling a liquid, very surprisingly, boiling a liquid is endothermic. And I just erased that. And it is endothermic. And the reason it's endothermic is because when you boil a liquid, you take the water, which is relatively close together, and you're breaking off pieces. So you're stretching those bonds out. And as they stretch out, they lose energy. Right? So it loses kinetic energy. It turns to chemical potential energy. Now that gas molecule, that water vapor, that steam bouncing around, when it hits the surface, as it's hitting the surface, it's speeding back up and then colliding really hard and returning that heat back into the water. But if it boils and goes away, it's actually cooling the water off, which is why as soon as you stop heating the water, that process is endothermic and the water will start cooling right away. That extra heat is leaving and getting stretched out in those bonds. Right? So you have to keep heating it because it's an endothermic process. Otherwise, the water will cool itself off. If boiling was an exothermic process, it would create more heat, heating itself up, making itself boil more. And that would be like, well, that's crazy because then all water would boil all the time. All right, that's it. So this is the actual use of the Hess's law, and we have these guys pop up, and we're trying to find the delta H here of this reaction of graphite to diamond. So I know in the reactants I need to have graphite, in the products I have diamond. I need to use these two equations to get there. So when I look at this, I'm like, okay, so here's my graphite. It's already on the reactant side. That's good. But I've got this extra O2 and CO2 stuff I need to cancel out. Then I look down here and I say, okay, now I need a diamond. And I've got, okay, so here's diamond, but it's on the reactant side. So I know I'm going to have to flip this equation over so that I have diamond on the other side. So let's write these down real quick. So this one I know is going to stay the way it is. So carbon, and I'm just going to put here for GR for the graphite, plus O2 gives CO2. Now I'm saving some time by not putting all this gas stuff in there. It's sloppy. I don't feel good about it, but there it is. Now the way I like to do it, I like to keep my arrows lined up so I can clearly see what's product and reactant, even if they don't quite match. You'll see what I mean on this side. So here I know I got to have diamond on my reactant or my product side. So I actually need to flip this equation so I get diamonds over on the right. So I'm going to flip it and say, hey, the carbon of the diamond plus O2. Now I flipped it, so that's my products, and my reactants are CO2. So there's my products and reactant side. You can see it doesn't quite line up on this, but it's more important to have the arrows line up. It'll make life easier. So going back here, I need to write my delta H's down. So my enthalpy of reaction for this one did not change because I didn't do anything to this reaction. Bam, so it's going to just be negative 393.5 kilojoules. And my delta H for this one. Now this one, I actually flipped it over. The way it's written here, this is an exothermic reaction. When we take diamond, add oxygen to it. So basically, you light diamond on it. You get diamond really hot, it'll actually burn in oxygen and make CO2. It's a tragic loss of a diamond. So in house fires, people will have their diamonds in their safes, and they'll get super hot in the safe in the house fire, and the diamond will actually just burn. And they'll take it out, and all they'll have left is just the gold band, and all the diamonds are just gone, and they turn to CO2. It's an awful loss of a diamond. So the delta H here, because we reverse this reaction, goes from being negative to being positive. It's still the same amount. It is just positive now. And that's always true of enthalpy. When you reverse the reaction, the sign changes. Instead of being exothermic, it's endothermic. All right. So now I got to check to make sure things cancel out properly. I want to have nothing but graphite and diamond, and sure enough, O2 cancels O2, CO2 on this side cancels CO2 on that side. I'm left when I add these equations together. I'm left with just carbon of graphite on this side gives carbon to diamond on this side. And then so I just add these. I also just add the enthalpies together. So that ends up being, so my enthalpy here is negative 393.5 kilojoules per mole, or just kilojoules here actually, plus 395.4 kilojoules. So as written, the delta H of this equation is equal, I think, to 1.9, negative 1.9 kilojoules. Now, as it's written, there's only 1 mole of this and 1 mole of this, so it's also per mole of anything in there. So I can write my delta H as that. That's how to do that problem. So here the only trick was to actually reverse this second equation. All right, next problem. So in this problem, we want to find the enthalpy of PCl5 going to PCl3 plus Cl2, and this is really phosphorus pentachloride and phosphorus trichloride and chlorine gas. So we're going to play with these equations some to kind of get there. So how do we do this? So I know I'm going to need PCl5 on the reactant side of the equation, so I'm going to find a PCl5 in here, and that's the only one right there. So I know right away I'm going to have to reverse this reaction because I want this on the reactant side. And then I also need PCl3 in here somewhere. I'm going to find it over here, and that's the only one right there. So this one needs to be on the product. I think I said reactant. This needs to be on the product side, and it already is, so that one's solid like that. And I also need some chlorine gas, and I see there's chlorine here and here. I'm going to trust that it just works out, because they're in 2 places. I'm going to hope it just works out when I reverse this bottom one. So let's write this down. So we have P4 plus 6Cl2 gives 4 phosphorus trichlorides, and the delta H of that reaction, enthalpy of that reaction, is negative 2,439 kilojoules. Okay, so as written, that's how many kilojoules you get. And this one we said we have to reverse because we want the PCl5 on the reactant side. So I'm going to put my arrow here, and I'm going to say, okay, so it's 4 PCl, or phosphorus or pentachloride, and that's going to give me 4 phosphorus plus 10 chlorine, just like that. And here my delta H, because I reversed my reaction, my delta H can go from being negative to being positive, and that's going to equal a positive 3,438 kilojoules. Awesome. Now let's see what happens. We may have to play a little bit more with this. I'm not sure. We want 1 PCl5, and it looks like we have 4 PCl5s here. And then let's see, P4s need to cancel. Yeah, let's see what happens. So let's just cancel stuff. So P4 cancels P4, right? And then 4 PCl5 is here. 6 Cl2s cancel, and that cancels 6 of these, leaving 4 Cl2s here. And then, yeah, let's add this all together. Woo, that's a terrible, that was a terrible line. So I end up with 4P, let me erase that. I end up with 4 PCl5 yields 4 PCl3 plus 4 Cl2. And that's going to equal, let's see, we didn't mess with anything, we just canceled things out. So that's going to equal these two added together. But now if you notice here, I actually divide all of this by 4. I have 4 times more than I need in my problem. I need a 1, a 1, and a 1. So all I'm going to do is divide this by 4. So this becomes a 1, this becomes a 1, this becomes a 1. Now that means if I divide this by 4, I'm going to have to divide all of this by 4 as well. So my delta H here becomes negative 2439 kilojoules plus 3438 kilojoules, right? And now that would be the amount, the enthalpy change if it was 4, 4, and 4. But I want 1, 1, and 1 for this problem. So I'm simply going to divide this number here by 4. I haven't done this math yet, so let's punch it in real quick. So we're going to look at negative 2439 plus 3438 equals divided by 4. We get an answer of like 250. I have 4 sig figs, so 249.8, 49.8 kilojoules for this reaction. So that last step was a little bit tricky. When we added them together, we had 4 times too many. So we had to divide our total enthalpy by 4 to get 4 times less energy from 4 times less reactant. I hope that's okay. Next one. I'm just going to work through these. I haven't done it before. I'm just going to... All right, so here we are on problem 9, and we're trying to figure out the enthalpy reaction for this overall reaction. This one looks like it's going to be a little bit complicated. Let's see if we can't go through it in sort of a logical approach. So the first thing I like to do is to figure out where everything is and whether I need to flip reactions or not. So I know I need a CO2 on the reactant side of the equation. So I look down here and there's my only CO2. So I know right away I've got to flip this equation because I know I'm going to need this CO2 over on the reactant side. So this one's getting flipped for sure. And then I look up here and I say, okay, boom, C2H, oh, I need H2O as well on the reactant side. And I see that I've got an H2O here and an H2O here. And I'm like, ooh, I don't want to figure out that yet. So I'm gonna wait on that and see what happens. So I'll leave this one alone for now, and then if I need to flip it, I always can later. And then the next thing I need to see is I need C2H2 on the product side. So I find here's my only C2H2 right here. I need to flip this one as well because I need this on the products. Right now it's on the reactants. So that's going to flip this one. And then I need some O2. When I look down here, I go, oh, O2 here, and there's O2 here. So we will deal with that when we get to it. Yeah? So again, this one might be one of those where something has to flip in here. For now, I'm going to leave this reaction alone. If I need to later, I can flip it once I see everything else working. All right, so let's write these down. So I'm going to flip this one, and I'm going to say C2H6. I'm going to leave some space here so I can keep my arrows lined up vertically. Leave some space on the reactant side. Goes C2H2, so dicarbon dihydride plus 2 hydrogens, and that's all happy times. Yep. And the delta H here, because I flipped it, is going to be the opposite. So instead of being negative, it's going to be positive. So instead of being exothermic, it's endothermic, and this is kilojoules. And then I know I'm going to flip this bottom one. I'm actually going to write that one next and leave that water one alone for just now and see kind of what happens. So C2, whoops, that is not right. Get rid of those. That was not right either. Come back to this guy. Here we go. And I'm going to flip this one, so I'm going to start over here and say 2 CO2s plus 3 H2Os. It's probably obvious to you, but it's really important at this point to make sure you get all the coefficients written down correctly. If you make a mistake on the coefficients, nothing is going to work out. It's going to be super frustrating. And again, I flip this one, so my delta H goes from being negative to positive. So delta H is equal to 283 kilojoules, and it's a positive now instead of a negative. Awesome. Now as I look at this, I'm like, okay, good. It looks like the C2H6s are going to cancel out nicely, right? And let's see, on this side, I need to have 2 waters, and I have 3. So I'm going to need to cancel some of this water. So yeah, it looks like I'm going to need to have one of these waters on the other side to cancel out. And I also need to cancel out the H2s, which I'm going to need some on the reactant side, and that would work here too. So this one must be a flip as well. And I noticed that by writing down the first 2 in the flipped orientation, the correct orientation, and seeing where I'm going to need more water, hydrogen, or oxygen. So let's write this next one down. We'll flip it as well. So this one is going to be H2 plus 1/2 O2 yields H2O. Awesome. And this is 7 halves. I don't know if that looks like an 8 or not, so let's put it, make it clear. And yeah, the coefficients are okay. And the delta H here, again, we reverse this reaction, so it's going to be going from a positive to a negative, and it's negative 71.2 kilojoules. Awesome. So now let's get started figuring these things out. So first of all, I want to look at what's going to need to cancel. So I'm going to need to cancel out, there's no hydrogen up here. So first I know I'm going to cancel this 2H2, so I need to do a 2 here. But if I double this one, I've got to double this one. Oops. And 2 times 1/2 is 1, and then 2 waters as well. And if I double the number of moles I have of this reaction, that's going to double the amount of energy the reaction produces. I'm going to put a 2 here as well. So that doubles my delta H. All right, so far so good. Now I need to, let's see, I need to have my C2H6s cancel, which they appear to cancel right now, because they're not in the problem, so that's good. I won't slash them yet until I figure everything else out. In the end, I need to have 2 CO2s in the reactant side, and right now I have 2 CO2s. That makes me happy. I need to have 2 waters, and I've got 3 waters here and 2 waters here. That's only 1 water, so that's going to be problematic. We're going to deal with that in a little bit. Over on this side, I need to have 2 C2H2s, and I only have 1. So maybe right away I say, okay, you know what I need to do? I need to double this one. And if I double this, I have to double this, and this turns into 4. So far so good. I doubled this, so now I need to double this one. But then I say, oh my gosh, look, that messed up my hydrogen. So I need 4 hydrogens here, 4 H2, so a total of 8 hydrogens, I should say. So down here I'm going to say, okay, I got to double this one again. So this becomes a 4, this becomes a 2, this becomes a 4. Woo, this is becoming a big mess. And now, so I had double multiplied by 2, I multiplied by 2 again. So 2 times 2 on this one. This is just the way it works. You just got to work through until you get everything to balance out right. So now I've got C2H6. Oh no, but now this one doesn't cancel that one. So now I got to double this one. Uh-oh. 4 CO2, 6 H2O, 2 of these, and 7 of those. So that's doubling everybody on this one. And that means I need to double the energy on this one. Now I'm really hoping this works out. We'll see. So C2H6 cancel, C2H6 cancel, 4 hydrogens cancel, 4 hydrogens cancel. It looks like we have 6 waters here and 4 waters here, leaving me 2 waters on, oh, I think it's going to work. We were confident. We held in there long enough. I think this is going to all work. Let's take a look. So my C2H6, now that I'm confident that I have some good stuff, I'm going to start canceling things. So C2H6 with C2H6. 4 hydrogens with 4 hydrogens. Let's see, 6 waters here, 4 waters here. So these 4 cancel some of these, leaving 2 waters left over. And, ooh, oxygens. So 2 and 7. So my 2 oxygens cancel with these 7, leaving 5. Woo, let's add these and see what happens. So I've got 4 CO2s left over here. Uh-oh. Uh-oh, that's not good. 4 CO2s, did I screw something up? Plus 2 H2O, give 2 C2H2, plus 5 O2s. Oh shoot, now I'm really confused. I don't think this problem is correct. I think there's a mistake somewhere, but I don't know where. Oh, it's here. Check this out. This is not balanced properly. This should be a 4. So the problem is wrong in that way. I apologize. I'll get that fixed. So this should be a 4 because if there's 2 C2s here, there has to be 4 carbons here. Something there's a typo on the worksheet. I super apologize for that. But this is, in the end, the way it should go. And our delta H here is a little bit complicated. So our total delta H is just the sum of all these things we've done. So 2 times 94.5 kilojoules plus 2 times 283 kilojoules plus 2 times 2 is 4 times negative 71.2 kilojoules, and that is equal to, let's do it, 2 times 94.5 plus 2 times 283 plus 4 times negative 71.2, and all of that is equal to a positive 470.2 kilojoules as the reaction is written right here, 4225. Awesome. That's that final problem. This is an endothermic reaction, so the bonds are being stretched. So the bonds in the products here, in the C2H2 and the 5O2, are actually stretched out, longer bonds than they would be without. Yay! 2 more problems to go, only like in half an hour. So problem number 11, let's do it. Right here's problem number 11. Whoops. There it is. Now in this one, I noticed I need sulfuric acid in the reactants, and I'm trying to find it. Here it is. It's in the products. I'm going to flip this one. So I know I'm going to flip this equation. I need SO3 in the products, and here it is in the products. So I'm not going to flip this one. Not. And here I need H2O in the products, and it's a gas. So I have H2O gas here in the products. And this liquid thing is going to have to cancel somewhere. It takes energy to take water from a liquid to a gas, and you have to include that in the enthalpy, because when this reaction formed, it snapped the water away from each other, and they were formed as a gas, so you have to take that into account, that endothermic process of pulling them apart, right? And so this one's a not as well, right? So my gas is on the product side. So let's write these guys down. So this first one I'm going to say is H2SO4, and that is going to H2S plus 2O2, and the delta H here, since we flipped it, is opposite, so it ends up being positive 235.5 kilojoules. And this one's not flipped, so this one's just going to be H2S plus 2O2. Here is SO3 plus H2O. And now I'm going to put liquid, because otherwise I'm going to have a hard time telling the liquid to gas. I can't keep being lazy in this case. And my last one here is going to be H2O liquid goes to H2O gas. All right. Oh, let me write these down. So these two are not flipped, so the delta H doesn't change. The enthalpy of change stays the same, negative 207 kilojoules. And my delta H here is equal to a positive 44 kilojoules. All right. So let's see what starts to cancel. So we need to cancel the H2S, which seems to cancel just fine. The 2O2s need to be gone, and they're gone. The SO3, there's one of them. There's one H2SO4. The liquid water cancels. I think it's ready. I think we're done. I don't think we have to do anything to it now. Well, this one's a lot easier than the last one, I tell you. So H2S cancels H2S. 2O2s cancel 2O2s. H2O liquid cancels H2O liquid. And I believe that's our reaction. So we have what's left over is H2SO4 yields H2O gas plus SO3, and I didn't put it in the same order, but it's still the same thing, and all the coefficients work out. So my delta H here is simply the sum of these three written as they are. So 235.5 kilojoules plus a negative 207 kilojoules plus 44 kilojoules, and that's going to end up being 235.5 plus negative 207 plus 44. That gives me 72.5 kilojoules. So again, this process is endothermic. As we pull and stretch those bonds farther apart, they convert that thermal energy into chemical potential energy. Awesome. Last problem we're doing together. Yay, the crowd said. Okay, it looks like it's going to be brutal. Nice. All right, so I start out finding my N2s as a gas, and here's an N2. Any other N2s? This one might be more complicated. No, awesome. So this N2 should be in the reactant side, so this is a not flipped problem. So I'll leave that one alone. I need to find all my O2s, and O2s are oftentimes in more than one place, but not in this case. They're right here. Now I need my O2 to be a reactant, so I'm going to have to flip this problem. Make it into a reactant. And NO2, I go find it, and it should be a product, and it's on the product side, so this is a not flipped problem. And let's write these down then. So not flipped, N2 plus 3H2 yields 2NH3, so the production of ammonia here. And then this not flipped one will be 2NH3 plus 4H2O gives off 2NO2 plus 7H2. That's not flipped as well. And this last one, oh, let me do the enthalpies here, sorry. Delta H is equal to negative 115 kilojoules. And this delta H is equal to negative 142.5. Oddly detailed number there. I don't know why I put the decimal place on there. Not good thinking. And then this one we're going to flip. So we're going to say, hey, the 1/2 O2 is over here plus H2 yields H2O, and this one is a delta H. And because we flipped it, the delta H changes, so it's equal to 43.7 kilojoules, which is really should be the same number as the last one, the 44. I just rounded the other one, didn't round this one. So if you're wondering why those numbers are different for the same reaction, they really shouldn't be. I should round the same. All right. I just got a text. Sorry, I did the same thing you do in class. I was like, ooh. I'll try and sneak a text back to her. All right, really sneaky on my part. So let's get back to what we were doing. So we need everything but nitrogen, oxygen, and nitrogen dioxide to cancel. So I need to get this 3H2 out of here. And I see that I have 7H2 here and 3 here. Okay, so that one looks really tricky to me. So I'm going to skip that and come back to it. It might just work itself out. And I need to get the NH3s gone as well. And these NH3s do cancel nicely, so I'm kind of happy about that, but still worried about these H2s. I also need to get the O2s to be 2 on the left side. And this is my only O2, so ooh, I can do that right away. So to get this 1/2 to be 2, I have to multiply by 4. So 4 here, and wait, multiply by 4. So 4 times 1/2. This really should be 2. My apologies. So 2O2, 4H2, 4 waters. I multiplied everything here by 4, so right away I'm going to put a 4 over here so I don't forget later. So I have 4 times the enthalpy because I have 4 times as much stuff here. Or I should say 4 times the enthalpy change. Okay, so did that help my H2 problem? It did. So I have 7H2 now and 7H2. So when something looks hard, have a little faith it'll work out. Chemistry almost always just works out if you have faith. And so I think that might do it. Let's just start canceling things and see what happens. Now, if I went through and started canceling things and noticed I needed to double or triple something else, I'd want to first go back and uncancel stuff because it really gets tricky with how to double things. So don't double after you've canceled. Wait till you cancel, then double. Wait till you make sure everything's doubled properly, then cancel afterwards. All right, so I have 7 H2s on this side, so 3 here, 4 here, cancel these 7 H2s. That worked out great. My 2 NH3s cancel these 2 NH3s, so that works out great. I've got 4 waters here and 4 waters here. That, if I'm convinced properly, looks like perfect. So I've got an N2 here. I've got 2 O2s here. Leave me with 2 NO2, and that equation matches this one. So now I need to do is just sum all of these delta H's together. So my delta H is equal to negative 115 kilojoules plus a negative 142.5 kilojoules plus 43.7 kilojoules times 4. And all of that together, so I take negative 115 plus negative 142.5 plus 43.7 times 4 is equal to, and we get, ta-da, negative 82.7 kilojoules for the equation as written here. So for 1 mole of nitrogen, you get this many kilojoules of energy. For 1 mole of oxygen, you get half this much energy because you only use half the nitrogen to do that. And the same thing with NO2, you get half this energy for 1 mole. Awesome, that's all the problems that I'm going to do for you today. I hope this video is not 3 hours long. Have a good evening. Bye-bye.